For this example, we're asked to look at a bending beam, which is pinned to ground over there on the left-hand side at x equal to 0. On the right-hand side, the beam is supported by a spring of stiffness k. So you might think of this as being like a simply supported beam, where the support on the right side is flexible, with the support on the left-hand side is non-flexible. The equation of motion for a beam, which is constant properties along its length. It's our usual EI, fourth derivative of the transverse displacement W, plus rho A, second derivative W with respect to time, and the right-hand side of that is a 0 because we're looking for free vibration. The solution. It's going to be the separable form that we've used many times before. We have W of x times T of t. You substitute that into the equation of motion. You separate out the x dependence on the left-hand side. And the time dependent there on the right-hand side, that becomes T double dot of t divided by t. We know that this is strictly a function of x. This is strictly a function of time. So the way the left equals right side is if they're both equal to the same constant there. I'm going to write that as the minus number of minus omega squared. So the same stuff. We have t double dot plus omega squared t. That's the time-dependent part that's given by, for free response, that's going to be c cosine plus s sine. And the spatial part is the fourth derivative of w plus rho a over ei omega squared. That's the parameter we've been calling beta to the fourth, times w is a 0. As we've seen in earlier examples, this says that the solution for a boundary value problem here is made up of hyperbolic cosine, hyperbolic sine, cosine, and sine. We impose our boundary conditions. So the boundary conditions that we will enforce are going to be a 0 displacement at the pin joint there on the left-hand side. So with our separable solution that we've written out, that being equal to a 0, it says that the spatial part at x equal to 0 is a 0. So we simply have a plus c is a 0. So therefore a is equal to minus c, and that's our first equation. We have the moment-free condition there on the left-hand side, ei, the second partial w with respect to x, on the left-hand side, written out in our separable form of ei double prime at 0 t of t. That's equal to 0, so therefore what we know is that this tells us that the w double prime on the left-hand side is a 0. So that gives us beta squared times the quantity c, a minus c, yes, a minus c is a 0. And so therefore if I take equations 1 and 2, in fact this is what I meant to use for equation 2. I use equations 1 and 2, along with the assumption that beta is not equal to a 0. This says that a and c both are equal to a 0. So they're on the right-hand side. Right-hand side, it's a moment-free condition, so that's ei second partial w with respect to x at x equal to L. The separable form of the solution is W double prime at L T of T, moment free, that's equal to a 0. So therefore we see that the second derivative of W with respect to x at x equal to L, that's a 0. And so for what we have left, that's going to be beta squared times B times the sinh function of beta L minus D sine beta L. And therefore, for again, assuming for right now that beta is not equal to a 0, we get the ratio there of D over B to be equal to the sinh function divided by the sine function of beta L. And that's going to be my equation 3. Lastly, we have the spring boundary condition. So what I will do is I will draw a free body diagram of the point right on the end here where that spring is attached. So we know that our sign convention is to say that the shear force there is EI third partial W with respect to x at x equal to L. The sign convention of that is positively down. So whenever I draw then the free body diagram of the actual pin or piece of material that's actually holds the spring on the end, I have an equal and opposite force. And the spring is going to be putting a force with the spring stiffness K times the deflection at the right hand side. I draw the arrow down because positive deflection is up, and when the beam is deflected upward on the end, the spring force is acting downward. Summing forces of Y on this joint there on the right hand side, I've got EI, the shear force, third partial of W with respect to x at x equal to L, minus the spring force at x equal to L. That is a 0. That attachment point, we'll say, has very small mass. So written in terms of our separable form of the solution, that's EI, the third derivative of W with respect to x at x equal to L, times T of T, is balanced out on the right-hand side by the spring constant K, W on the right-hand side, T of T. So that must be true for all time. We can cancel out that T, and we get, therefore, the EI times the triple derivative of W, that's going to be a B cosh beta L minus D cosine beta L. This is just the third derivative of W with the beta cubed there. And on the right-hand side is K times B sinh beta L plus D sine beta L. That's a contribution coming from the displacement there on the right-hand side. So what I will do is I will group together my coefficients of B and D. The B's there on the left-hand side is going to be an EI beta cubed divided by K cosh beta L minus sine beta L times B. The right-hand side is what I have when I group together my coefficients in front of D. So that's going to be EI beta cubed divided by K times cosine beta L plus sine beta L. I need to make a correction on what I did above. This term here should be the sinh. Also, from above, we have seen that that D over B is given by the ratio of the sinh to the sine. So I'll put that relationship in here. So D then is equal to sinh beta L divided by sine beta L times B. So what this means is whenever I group together my terms, I'll do this in a couple steps to make sure that we're following along here. It's going to be alpha beta L cubed cosh beta L minus sinh beta L times sine beta L, basically multiplied both sides by sine beta L. And on the right hand side I have alpha beta L cubed times cosine beta L plus sine beta L times sinh. Okay, where I've defined alpha to be the shorthand notation for EI divided by KL cubed. Okay, now what I'll do, just to simplify this a little more, is I'm going to divide both sides by cosine beta L, sinh beta L. Again, my goal here is to slightly simplify things. So when I divide both sides by that, what I end up with is a characteristic equation that looks like this. Alpha beta L cubed co-hyperbolic tangent beta L minus 2 times tan beta L is equal to alpha beta L cubed. So this is our characteristic equation. A little bit more involved than any other problem that we have done. And it's very clear, based on what we've seen before, that there's not going to be a closed form solution for this. So what we will do is our usual thing. We'll make a sketch of the characteristic functions. More involved because we've actually got 3 of them. We have a co-hyperbolic tan, we have a regular tan, and then we have a beta L cubed. But we'll make a drawing of those as a function of beta L. And based on this sketch, we will be able to estimate the location of the roots using our sketch. That's the power of drawing that sketch. We will use the solver in MATLAB to determine the roots of the characteristic equation. And of course, we will get our natural frequencies from the usual relationship of beta JL squared times the square root of EI over rho AL to the fourth, just like we have on all the other problems we have done. Our modal functions, we know we need to finish up on that because we have to sort of combine some ideas here. Wj of x, that is, as we know, is aj cosine beta jx plus bj, trying to go too fast here, this is the hyperbolic cosine beta jx plus bj hyperbolic sine plus cj cosine plus dj sine. What we found were that aj coefficients were 0, so were the cj's. And if we use the relationship above, we see that we can write this as bj times hyperbolic sine beta jx plus sinh beta jl divided by sine beta jl times sine beta jx. So these are our modal functions. At this point, bj's, those are arbitrary, non-zero coefficients. What we'll do is set those equal to 1. And so those are our modal functions. It's probably worth our while to check our results. And that is, as I mentioned at the beginning, this problem might represent a simply supported beam where the support on the right-hand side is compliant. But if we let the compliancy go to a 0, the stiffness go to infinity in this case, we should be able to resurrect the frequencies for the simply supported beam. Is that true? Well, we know that as k becomes infinitely large, it says that our parameter there of alpha, which we define as ei over kl cubed, this goes to a 0. So our characteristic equation identified above becomes tan beta L equal to a 0, which means that the beta JLs equal to J pi, which means that omega J's then J pi squared over times the square root of EI over rho A L to the 4th. And that's good. And our modal functions go to sine of J pi x over L as they should. So this problem, very similar to all the other beam problems we've done up to this point. We start out with the general form of the solution of the boundary value problem written in terms of coshs, sinh, cosines, and sines, enforce our boundary conditions. We get our natural frequencies and mode shapes.